Okay, so you can see this is a VL equal to di by dt. So or we can write this voltage across the inductor equal to L into di by dt. Okay, so that is nothing but this is a storage element. Okay, I said in the initial stage. Okay, resistor will dissipates the energy always, and inductor and capacitors both are stores the energy. Okay, so for ideal DC supply, so this will be 0. Okay, for ideal DC supply this will be 0, because you know the DC means, so the difference between DC and AC you should know it that. So DC will be constant over the period of time, so constant up to infinite period of time. So if the signal is like this, if the signal is like this, so the constant period, okay, if the current is like constant in the DC case. Okay, so if you divide this one, so what you will get, you will get the 0 only, because it's a constant value. So always if you do a constant value, so here you will get the some value only directly. If this is the some 5, so current I is here, it is a 5. So if you divide this with respect to time, so you will get the value is 0. Mathematically also you can prove this one. So why this di by dt is 0? So according to the mathematical equation also I can show you that. Okay, so now just see here. So this is a VL equal to 0. VL equal to 0, that is nothing but inductor is a short circuit for a ideal DC in a steady state. Okay, why we are calling a steady state? So steady state is nothing but, so initial state is when t is time is 0 or 0 plus or 0 minus. So that will comes in the transient part, 0 plus 0 minus or t equal to 0. So all these are the initial conditions. Okay, when t equal to infinity, we can say that is a steady state condition. Okay, steady state means infinite period of time. So if you see, inductor is a short circuit for ideal DC in steady state. See here, for ideal t equal to infinity also, so this will be 0 for a DC current. Okay, so when it is AC, so in AC this waveform will be like this. Okay, so this is time varying current. So here the equation for current is I equal to some Im into sine omega t. So if you divide this di by dt, so you won't get 0 in this AC case, only for DC. So this VL is 0, or you can see using a Laplace transform. Okay, we can write this di by dt. So we can write this VL equal to L into this di by dt, we can write as a j omega into I. Okay, so you can, if you expand this omega, so L into j into 2 pi f into I. Okay, so for DC you will know that, so that frequency is 0 for DC value. So if you substitute that 0, so you are getting anyways 0. Okay, so anyways you can get to know that, so for DC values the VL voltage across the inductor is 0. So that means, so the inductor will be short for DC supply. Okay, and see, sudden change means this is within the short time. Okay, within the short time, so that won't change. Okay, so that means Vi implies infinity. Okay, we can't produce an infinite period of time. So if the di by dt, so if the short time means almost 0 time. Okay, short time means almost 0 time. If the 0 time, the formula is L into di by dt. So if this dt is 0, because it's a small time, if I'm taking it's a very small time, so it is 0. So 1 by 0 something is infinity. So in the short time we can't produce this infinite voltage in the inductor. Okay, so that is against the law of conservation of energy, because if you are producing within a second, if you are producing infinite period of voltage, so that means you are producing a high energy. So if you are able to producing that energy, that means it's a miracle. So that is, I mean, that is not a valid case, that is against a law of conservation of energy, so that won't be possible in any case. So that's why sudden change means in a small period of time it won't act properly. So that means it won't change suddenly. Okay, it won't change it for sudden change of a currents. Okay, so that means, okay, it against a law of conservation of energy. And ideal inductor is coiled wire with a zero internal resistance. So power loss is zero across the ideal resistance. Okay, so I will show you. Here you can see this is the inductor part. Okay, this is the inductor part, ideal for ideal inductor, and this is a small r. Okay, if you say it is a small r, if it is 0, then it is a ideal inductor. Okay, because ideal inductor will not have any internal resistances. Okay, so that means no power loss inside the ideal inductor. Okay, so but normally practical inductor will have some resistance here, will have some resistance here. Okay, this is the equivalent circuit of a ideal inductor, and as well as the, okay, mutually I have explained here. Okay, so inductors are available in different shapes, in sizes, and they are classified based on the type of core material on which winding is done. Okay, so we have a different kind of inductors in the market. So different shapes and sizes, they are classified based on the type of winding is done. So inside which type of winding is done depends on that we can classify which type of inductor it is. Okay, so practical inductors have a small internal resistance and they have a represented by a coil shown here. Okay, so you can see for practical, so some resistance will be there in for practical case. For ideal case this will be 0. Okay, now see the capacitor. Okay, inductor will not allow the sudden change of a current. Okay, capacitor will not allow the sudden change of a voltage. Okay, because here I equal to C into dV by dt. Okay, if it is in a short time of dt equal to 0, so I will be okay, that I will, okay. So I will explain this point later, but here I want to say for the DC supply. For DC supply dV by dt is 0. So in that case IC is 0. So capacitor act as a open circuit for ideal DC in a steady state. Okay, so for DC value, okay, inductor acting like a short circuit, capacitor acting like a open circuit. Okay, remember those 2 points. Those are very important in our transient theorem, transients problems. Okay, so all the transients we apply these conditions only. Okay, so this DC is nothing but frequency is 0. Frequency is nothing but SR omega equal to 0. Okay, S is nothing but a j omega, right? Okay, so here omega is 0, frequency is 0 for DC value. So like that we analyze all the things. Okay, all the things we analyze it. So now capacitor will not allow sudden change in voltage across it. Okay, so ideal capacitors are considered to have a infinite dielectric. Okay, so normally you can see here infinite dielectric, that means this is open, right? This is open across this ideal capacitor, because of here resistance is infinity. Because open circuit always we can say that is a resistance of infinity. For practical case we'll have some leakage that we can represent with some small resistance. Okay, so that is the difference between the ideal and practical cases.